Okay, so it's about time to start, so please take a seat. Okay, so first of all, I would like to thank everyone for coming and also to the Simon Center for hosting us here. It is my pleasure to introduce Professor Yitang Zhang from University of New Hampshire, visiting Institute of Advanced Studies this semester. He will talk about small gaps for prime numbers, which is of course connected to the twin prime number conjecture. And for this work, he was recognized with many prizes recently, including the Cole Prize for Algebra, the Ostrov Prize, the Schock Prize, the Morningside Prize, and he will give a special lecture at the ICM in August in Seoul. So we have the pleasure to hear this before the ICM. So without further interruption, let's start. Thank you.
Thank you. First, can you hear me? Okay, no problem. Good. I may make a small change on the title. We say the bounded gaps. We don't say small gaps. Small, how small? But sure, at least it should be less than infinity, right? But less than infinity in mathematics, we understand that it is bounded. So we say bounded gaps. I'm not going to state the twin prime conjecture again, but we know the result. I just say the main result. That's the bounded gaps is, we say they are infinitely many prime pairs we say PQ such that Q minus P is less than a constant. The n could be a large constant, but it is a constant. But this is not enough. If I just say, we may say this is a trivial. If Q equal to P, so let me add one thing here. Of course, otherwise we have nothing to prove, right? And we say, how can we get the ideas, then how can we start to prove such a one? Here, I first mentioned, yesterday I checked with some friends. Is it okay to say something maybe too technical in detail? This is analytic number theory. Something could be very technical in detail. I try to avoid something like this. But we emphasize one thing, the basic idea. In particular, this is the feature maybe, or the features of the analytic number theory. Even we say number theory, algebraic number theory, the treatment something are totally different. Let me mention it. Then how can we prove this? Actually, there are several approaches. But till now, the very successful approach is from a more general conjecture. Then we consider the special case of that conjecture. I say mostly the most successful approach, but it may not be the best approach. In number theory, maybe everything is possible. So how can we say I have to introduce something like this with the basic notation. We say H is a finite set of non-negative integers. Maybe we allowed it to be 0. So we say H is admissible. Means what? Means for every prime P, there exists, and I just say this is the integer. such that I say the product is coprime to P. We say the product is coprime to P. P is a prime, so that means each factor n plus h1, n plus h2, each of them is coprime to P. Let's see some examples. If I just simply say something, the set is admissible, what means that? The definition is not too long, but let's see something like this. We say H consists of two numbers, 2, 3. Is this set admissible? We may say no. We know that's the very basic. If it is admissible, it just means for every prime P, we can find n such that. Now we say it is not admissible, non-admissible. We say we can find a prime P such that for every n, then this is not coprime to the P. I say not admissible, let me just say, because we can choose P equal to 2. Then for every n, let's see, n plus 2, n plus 3, exactly one of these two numbers for every n is divisible by 2. It's not, so the product is not coprime to 2. So we say this is 1 is divisible by 2. Now let's consider something a little more. This maybe is a little more, but it's still not complicated. Still we say no. We may choose P equal to 3. Then for every n, n plus 0, n itself, n plus 2, n plus 4, always the product, exactly one of them is divisible by 3. So no. Then we may say, this is not a no, that is no. Can we give a yes? Yes. And something more. Let me add one more. But we cannot add the 4. Let's add 6. Yes. Now I would like to state a general conjecture in number theory by Hardy-Littlewood. But let me say, maybe my statement is different and not essentially maybe the same as their conjecture or a part of their conjectures. But I just like to say, what is a conjecture? Hardy-Littlewood. Saying H is admissible if and only if they are, also let me say infinitely, many n such that all of the k numbers like this, totally it is k, n plus h1, n plus h2. All of these, or in other words, with each of these k numbers are primes. This is the Hardy-Littlewood conjecture. Of course, this is, I think this is very deep. Should be a very hard one. Why I say it's very deep? Actually, The simple example is we just take, we say H is admissible, we take H equal 2. Then we say each of these, but totally we have 2. N plus 0 and n plus r both prime. This is just a twin prime conjecture. So twin prime conjecture is a special case of the Hardy-Littlewood conjecture. And also, it's easy to say, to check that. We say if and only if, but the main part should be this implies there are infinitely many something. In that direction, actually, I say it is trivial. We may verify it. If there are infinitely many and such that these are all primes, then H must be admissible. So now we find that in concerning with the distribution of the primes, the existence of infinitely many primes, something like this. The definition of admissible set, it is should be natural. Yeah, it is natural. And also, this way give us one way. We try to prove the bounded gaps between primes. If we can we say the weak or weaker result or the partial result of the Hardy-Littlewood conjecture. This is what we have proved. That is, so we assume H is admissible. And also, it is a fixed set. So these numbers, H1, H2, we regard them as constants. And also, but here the K could be, K is large. In my paper, I required that K is greater than or equal to 3.5 million. But it is a constant, right? Then they are, let me repeat it, that's important, infinitely many, and such that, sorry, let me put a label here. This is label 1. Not all of these numbers, such at least 2 of the group of these K numbers this is what we proved. And we just easily we say there are infinitely many n such that at least 2 of these are primes. Then the gap between these, first let me say the H1, H2, these are distinct numbers, not a repeat. Okay, but that should be, we say at least 2 are primes. And the gap between these 2 primes, it is, of course it is bounded. Because this set, H is fixed. And there are infinitely many n such that at least 2. This is our basic idea of proof. To prove a partial result of the Hardy-Littlewood conjecture, that implies the bounded gaps. Now, can we say, how can we prove? Here, I would like to say, we try to just, I like to present something, the basic idea, basic technique in analytic number theory. Thus, we say maybe some of us learned something about analytic number theory. We may complain that there's so many sums, the sigma, right? First, we say these sums, Usually these sums, they are all finite sums, so we don't worry about the convergence. Of course, finite sums. We don't worry about changing the order of summation. That doesn't matter. But sometimes it is very technical. So now we say, how can we start? And we assume H is fixed. It is admissible. We fixed it. And X is a large number. We say arbitrary.
How would you construct an arbitrarily large admissible set?
It is a proof that the existence of that, and even in a certain range, how many we can approximately just estimate. But a very simple way is like this. So we say to construct H admissible. So first, given K, we say H1, H2 to HK. They are all primes, but the smallest is greater than K. These are K primes, and each of which is greater than the given K. Then, in this case, they are all primes. In this case, we can prove this set is admissible. Then you may try it. It's not difficult. Actually, my bound, the 70 million, something like this, I just used this one. I didn't know how to construct it or get something more precise, but I just used it. That makes sense? Thank you. So X is a large number. Actually, usually we just consider we fix some things, the set. We let X approaching infinity. Approaching infinity. Then we introduce something like this. Here, I like to introduce a function defined on the positive integers. We may complain this definition is very strange, but it is reasonable because the prime numbers are involved. We try to formulate the process. So it is equal to 1 if m is a prime. Otherwise, if m is not prime, it is equal to 0. This is just the characteristic function of the prime numbers. So now let's see. Just a second. I remember it, but I may not be able to remember the labels of the formulas. We start in this. We claim there exists an n which is greater than x, and maybe the upper bound is 2x or 3x or 5x. That doesn't matter. Such that this is summation. If we look at, oh, this is greater than 1, but we know that because in this sum, every term is an integer, either is 0 or 1. So totally it is an integer. This integer is greater than 1. just means this just implies all the same as this summation. The sum is greater than or equal to 2. So this just because x is arbitrarily large, always we have n between x. So this just implies at least 2 of these are primes. So we try to find that there exists at least one n such that this one, it is a function in n, is positive. And the n is between x and 2x. Then the next, how can we do? That is very crucial. We try to construct some functions. Then we need to here, that is the basic ideas of the 3 mathematicians got Stone, Pins, and Yildirim. Their idea is to translate into evaluating certain sums, verify this sum satisfies in some positive condition. That is to construct a function, f of n. This function, no constraint. It is whatever it is, you can take it, but only one thing. It is non-negative. And to show that, this is non-negative here. Originally, we try to prove there exists n such that this function in n is positive. Then how can we do that? We try to construct a function, non-negative, to show this sum over n is positive. Then that's all. Because this is non-negative, if it is positive, at least one term is positive. But this, of course, it is also positive, non-zero. Then this is positive. Now, how can we construct this function? We may consider, let's say some function, n is a constant. F of n identity just equal to 1. You may try it. We just need to construct a function such as this, but maybe we may try various functions to see what happened. Usually it does not work. Now let me say a very safe way, an extreme case. It always works. Why? We say, f of n is equal to 1 and 0. It is equal to 1 if the sum if it is equal to 0, it is less than or equal to 0. Do you think this works? This one, of course, this gives us one thing. The sum could be taken such that it is non-negative, greater than or equal to 0. Yeah, it could be equal to greater than or equal to 0, but it's not guaranteed, say this is strictly greater than 0. But the second example tells us what? We say to construct a function which is non-negative and show that, we have to show that. That means that's a sum. Here the ik is a constant fixed, n from x to 2x, that's a big sum. We should be able to evaluate it. And then we can check the result. Then for which choice of n, f of n, we are able to evaluate it. And then that should be the very deep problems in analytic number theory. And here, actually, it involves all the basic ideas and methods in the so-called, that's called the sieve method in number theory, like this. And it took got stone pins and yttrium maybe more than 10 years. Eventually they found a very just appropriate form of the f of n. I'm happy we have so many boards. I like to use boards. I never like to use the projector or something like this. I prefer to write down everything. So we say choosing. I just use this one. It's called the stone pins yttrium sieve. That's like this. We have to introduce something. I like let the capital P of n, let this present the product of the n plus h. And we introduce, I'm not going to repeat the basic definition. This is a very basic function in number theory. This is so-called Mobius function, like this. And also, that is, we need to choose a function, but this function in analytic number theory, we say we need to choose a function. We try to look at what should be the proper form of the function. Then we write down this form. But this form is not just a precise way. That may involve some other functions. That could be simpler. And so this involves some other function. I say g of d. For g of d, only thing is we require it to be, it is a real function. We don't worry about the complex situation. Now, because the f of n should be non-negative, that was the first the idea by Serberg, the sieve. The function should be non-negative. We take it as a square form. It is the square of another real function, so it is non-negative. Then inside the base of this square, then in the sieve method, that I may not say something. Maybe too technical. The Mobius function is involved in the sieve. So they took this one. That is f of n is equal to, is a big square. Let me put a square here. Inside it is a summation over d. D runs through the divisors of this product with another constraint, that is d is less than capital D. And what is capital D? Capital D is a fixed power of the given x. Given x. Here the C is between. We will come back to this fixed exponent C again. That will be important. Now, the question still it remains. We say we choose something like this. And then the G of D, we have, usually G of D is relatively simple. I'm not going to say something more. Then how can we do? The question is, should we be able to evaluate it? We have certain, we have restrictions on this. And even if we evaluate it, can we find the result eventually we can show it is positive? That's also. So now, let's see. Results of got stone pins and the yield ring. That is. So we say the left side of the 3. Actually, it is, we may separate it into the 2 sums. N is between x and 2x. This is already formula 4. Is equal to precisely, it takes the form I'm not going to write down what is P1, what is P2, either. What is E? That's very difficult. I just say T1, T2, we have a factor x. T1 just arises from the first sum. That's complicated. And the T2 arises from the second term, the main term. E is the arrow. Then you may complain that you just write down the T1, T2. We say, myself, I can write down some, maybe C1, C2. What means that? Here, I apologize. I tried, actually, it's on my notes. But to write down, you may not be interested. It's too complicated. But let's say the result is. So we say, by the 5, we need to prove the formula 3. It should be clear. We say, that should be positive. We must have the main term, the coefficient, it is positive. The second one, the arrow, in comparison with the main term is small enough. So that is in analytic number theory, like the Goldbach conjecture or something like this. We need to prove something, the number of solutions of an equation is positive. Then we need to prove it is positive. We have various ways to write down the expressions. Then in the expressions, in order to prove positive, we must always we have something we call them the main term. The main term must be positive, at least the coefficient of the main term. We have x must be positive. Meanwhile, we should be able to control the error term. Now let's see what the results of that. I just say the result, just give this form. They prove that. Let's recall something here. We have a parameter which is a d, the x raised to c involved. C is a constant. So they prove that if C is greater than or equal to 1/4, here this is the C, and this is the D is here, capital D is here. If C is less than or equal to 1/4, then however we choose the G of D, the first requirements fails to hold. So that, in other words, we must have.
What's C?
What's C?
What is C?
Here we have the capital D, and I say D is the fixed power of x. The exponent is C. So I apologize, I should say something earlier. But I mentioned that everything will depend on the C. So because the A fails, we have nothing to do. But now, if C is greater than, strictly greater than, maybe just very slightly greater than, say maybe C is equal to 1/4 plus epsilon. Anyway, just give a small constant. Then but we say we have to choose with the G of D properly. So in other words, in order to satisfy the requirement A, whatever, we just need the C is equal to 1/4 plus epsilon. Then it's not so difficult to choose the D of D such that A is satisfied.
In the sum for equation 5, x?
Oh, yes, yes. I couldn't skip it, sorry. But of course, we just assume that. So we may say it is easier just for the C slightly greater than 1/4, maybe 1/4 plus epsilon. That's satisfied. Now, but we have a second requirement. The arrow E should be small. That's totally different. We say and here, that actually I was hesitating about that. Should I give some more precise the expression for the E, where the E comes from? This is the arrow term, but maybe it's so complicated. I just say about E, the result. If C is less than, even equal, that doesn't matter. Let me say this is small. This is the most, one of the greatest theorem in analytic number theory, the so-called Bambiri-Vinogradov. I said something in Russian, Vinogradov. I learned some Russian. But this is very, very strong. So C is greater than or equal to 1/4, something like this. That is a very difficult problem. What I can say is, even the generalized Riemann hypothesis does not help directly. Let me say directly.
Is the fourth related to the number in the generalized Riemann hypothesis?
Yeah, the generalized Riemann hypothesis here, I just say that in analytic number theory, just means the Riemann hypothesis for all Dirichlet the character the L functions. Anyway, just like this. Okay. And now let me say something about that. Actually, here we say C, because the F we have a square form. So actually, if we square out it, we get something that D1 times D2, then D1, D2 is less than the capital D squared is that. So we say C is less than 1/4, then 2C is less than 1/2. Otherwise, this is greater than 1/2. So in that way, that's a bigger gap here. Okay, but that's a very difficult one. And let me mention something. Bambiri-Vinogradov theorem was discovered in 65, almost 50 years ago, right? Then later on, around maybe 30 years ago, Bambiri, Friedland, Ioannich, they tried to do something to get it stronger. In our form, they tried to get something for C greater than 1/4. They developed a series of the methods, and also they got some partial results. But still in this way, C greater than 1/4, it is a very difficult one. I say even the generalized Riemann hypothesis does not help, but eventually, I think my major contribution is I overcome the major difficulty about this. Let's say my result first, it is technical. We say just we say with just a proper constraint on the function g of d, but that doesn't matter. That never changed. That has never changed a. E is small enough. Sorry, small. With. Oh, not with. For. C equal to they receive 1/4 greater than 1/4. Sorry. Let me rewrite it here. So now, in such a situation, although I impose some constraint on something technically, that doesn't matter. A is satisfied, and C is greater than 1/4. C. B is also satisfied. Then in this way, we prove we prove anyway this, of course it is positive. This is small enough. The absolute value is smaller, so it is positive. We prove. Sorry, it should be here. And maybe it is so rough. I tried to cover something more detailed. But here, let me mention something. That is a very interesting phenomenon. Usually we say we study the distribution of prime numbers, maybe prime numbers in arithmetic progressions or something. That's the so-called Pompeo-Vinogradov theorem concern. In natural way, the people believe that there should be the Dirichlet L functions and the Riemann zeta functions. And the Pompeo-Vinogradov theorem in this aspect, it is regarded as strong as the generalized Riemann hypothesis. So even we assume the generalized Riemann hypothesis, still we can get the Pompeo-Vinogradov theorem. It's the same. But let's say C is greater than 1/4, something like this. In my proof, it is very interesting. I didn't use any Dirichlet L function. Oh, I used just a little. It is implicitly contained. Use a little. In general, the problem is reduced to other types of the Riemann hypothesis in algebraic geometry. The Riemann hypothesis for varieties over finite fields. In the one-dimensional case, the curve case, it was proved by, still I don't know how to pronounce its name. Why? Right? Yeah, Wei. He proved that in a one-dimensional case. And actually, my proof reduced to the algebraic geometry. We need a result which is the two-dimensional case. Fortunately, it was proved by Deligne. Anyways, so we can use them to get these. And the last one is, I say with or under a proper constraint, not off, sorry, on. I get this. Now, just last month, from Iowa University, my friend showed me the best result is proved by the polymath. C could be taken. Of course, this is better than mine, right? And also at the very beginning, I mentioned that we say this method is very successful. Goldstone pins Yildirim's form. I take this way then. But we say it's successful, but maybe something better. Recently, another, I met him, Maynard, who got a stronger result. What he took is f of n. It must be non-negative, so still it is square. But now inside it's more complicated. We say we just take that one sum d. D runs through the divisors of the product of these one. He separates these things. Say it is a multiple. D1 divides n plus h1. D2 dividing n plus h2. And sorry, we need more space. But let me write down. We say da 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 da. dk dividing n plus hk. And also the product of d1 until the dk is less than d. This is a multiple summation. And here it is taken modulus D1, modulus D2 till modulus dk. And then, sorry, we need a little more space, right? It is, this is not in one variable, in k variables. This is proved better than, stronger than that. It is a general form, but it's more complicated. So just like this. The last one is, let me say. Last year, when I submit my paper, I didn't realize something more. Didn't realize that I would become just like very famous like here. But now, after learning some comments from others, maybe my methods here, we say the break, sometimes somewhat maybe stronger than the generalized Riemann hypothesis. That really opened a new door. And actually, there are many things we can do here. Thank you. Any question?
Okay, so that was a really beautiful talk. So let's see some questions. Okay.
Do you hear T1 and T2 is a function of n or just something independent of x?
Independent. Actually, it involves something like the x. It takes the form like this. Maybe involves something like the logarithm of x. So we say maybe T1 is equal to, we say the C1. This is a constant independent of x. Here maybe it's just powers of x. Usually they take something like this. A constant, then multiplied by the power, a fixed power of the logarithm of x.
So your statement A means T1 minus T2 should be larger than 0 for arbitrary x.
Yeah, actually it is true like this. I think right now, this is also logarithm. This is a positive power. So we say C1 minus T2 is greater than 0. This just means C1 minus T2. These are constants, right? The constants, the difference between these constants is positive.
So this is what your statement A means, right?
Right. Then we should take this form. Like that is a little. Anyway.
I have two very rudimentary questions. I'm not in math. So the first question is, do you have an estimation how large it is?
I didn't do it. Although it is not difficult to determine how large, but I didn't do it. Maybe the
Estimation how many digits in that number?
That should be yes. Actually, let me give you a very thing. We say that actually it is x and between the x and the 2x. That should be x equal to, we say the e raised to. This is enough. But of course, we may reduce it.
Sorry, I have another question. The second question is about distribution of prime numbers. So does this result actually imply that when you write prime numbers just one after the other, until you just keep writing, and they never go far apart from each other? Does this result imply that?
That says that on average they are going farther and more farther. But always there are some exceptions. They are very close. I just say there are infinitely many exceptions of the two pairs are very close to each other. Bounded.
How far away from the twin prime conjecture?
How far to reach? I think, if we use this approach, the twin prime conjecture actually, we should take a k equal to 2. There is some essential gaps. I think the current method does not cover, although I have been thinking about some other general forms, maybe something different. But anyway, I didn't success.
So you talked about Maynard, who's looking at other ways to construct FMN. To what extent do you think your results would be applicable, or you could apply your methods to other types of FMN?
Till now, actually, I think I say that my methods may apply to some other problems, but in the gaps between the prime gaps problems, maybe these methods, this is how we can go. We may not improve too much.
So the capital N, is that bounded or unbounded?
Capital N?
The large constant N. The Q minus P is less than N.
Oh, this is bounded. This is a constant.
Oh, okay.
Now it could take equal to maybe 600 or something like this. I write on the capital N here just to represent a constant. I don't know what, but it is a constant. It is bounded.
Could you give us some feeling why it is a good choice of the function f of n? So why this function is relevant to the problem?
The good choice of f of n, this, how can we say, we know from in the sieve methods, something we just like we are doing some experiments to try something to see. Theoretically, still it's not very neutral, something like this. So still there are some doors to further improve. And we take the square form that was discovered by Sarah. He said, oh, we need something non-negative. Okay, we say it is a square of something. Then let's determine the base. But to determine the base, anyway, even the choice like Formula 4, as I heard at IAS several years ago, Serberg himself was surprised by this choice. How could this work? But it really works. Now the Menardus is more efficient, but it's theoretically it's hard. It may not be easy to explain why this is good or that is not good.
You could have positive semi-definite functions which are not sums of squares. Have people ever used things like that?
Not squares?
So you could have functions which are positive semi-definite, but not sums of squares. So they're always positive, but you can't obviously write them as a sum of squares. Have people used
the square form? Let me say the first one that was before Serberg by another Norway mathematician, the Brook. It's called the Brook. He used the modules, but he used something without the square. But now we have some more conditions on the G of D. In certain conditions, this is all still non-negative, but it's very complicated. Then Serberg make the change. We just take the square. Now this could be very flexible. It is proved that Serberg's method, taking square, is much better than the Brock's. But still theoretically, it's hard to explain why. In practice, we found it's better.
It's not a sum of squares, it's a square of the sum.
Square of the sum.
Not a sum of squares.
Of course. If it is sum of square, maybe we know the square of the sum because the base is allowed to contain the many terms, so it's very flexible. If we take the square, onto this one. The first is the Mobius is almost, we don't need it. It just takes the maybe either 0 or 1, right? That's totally different. We should use the square of the sum instead of the sum of the squares.
Okay, so a question here.
You have this number 1 over 1,168. So is this like end of result? I mean, why you pick that number? I mean, just people have different numbers. So what's the philosophy behind the?
It's not a philosophy. What I choose this number is I find we need several requirements. The first requirement, the first one is that this we say. So we say C equal to 1/4 plus, in my notation, pi. We have several constraints on this one. The first is maybe pi is less than. The second, that must be less than. But each way, several finite many constraints. Each one is less than this, right? Then I just choose the smallest. Maybe the third is. Maybe less than something like this. So I just found that we just take something like this, and that's everything. But it was very rough. On my, if you read the instruction, introduction of my paper, the first section. The end is just saying that we have certain ways to reduce it, but that will not be discussed in this paper. Actually, that time I was so tired.
You mentioned the NANA, the new method of constructing FN. So, but does he also need to use your reduction to this Riemann hypothesis on finite field?
In his method, C equal to 1/4 is good enough. So he didn't use it. But if we used it something like this, of course, better results.
Yeah. Is there a reason why you choose that epsilon to be a rational number? Is there a reason why you choose that epsilon?
Absolutely.
The 1/4 plus something? Is there a reason why that something is rational?
Yeah, because the 1/4 is just a critical point like this. Less than 1/4.
Oh, no. I'm talking about the extra part after 1/4. So far, everything you have shown is for rational numbers, right? There's 1/100, 1/200.
Oh,
they're all rational. So
that was in my research. We needed to, in the paper, we needed to. We have several constraints. I list all these constraints. Then the stronger constraint, the very tough constraint is this. Then I choose that.
So is it harder to do it with irrational?
It's not too hard.
Okay, so I think there is an event here soon. Let's take a final question.
So how small of admissible sets meet this conjecture now?
Smaller. You say what?
Your K. Oh.
This one?
No.
K in my paper, I talk it is 3.5 million. Now it is because the bound is reduced to 6, maybe several hundred. Maybe now K is just 100 or something is enough. Maybe. I didn't check it.
So if you establish this result for a quarter plus something, do you get it between there and a quarter automatically? Does it also hold for all smaller numbers than a quarter plus 1/1168 and a quarter? So your choice of 1168 is somewhat arbitrary. There's a whole interval of values.
Actually, at the very beginning in my paper, I tried to just write down it's greater than it is equal to 1/4 plus epsilon. Greater than 1/4. Then here there exists the bounded something like this. But I didn't try to determine this value. Then I found it may not be very difficult at all. But I didn't do something very detailed. I just, 70 million is good enough. Okay. That's all. Because I was really tired at that time.
Okay, thank you very much again.
Thank you.